Let's review some of the things that you had to do yesterday to get to the point we we're at, and I'm going to draw it slightly different to help some of the folks who are having difficulty. Rather than having some wonky angle or anything like that, I'm going to try and line it up in a more Cartesian way so that perhaps it helps that will help benefit you. Don't assume that's the way it'll look up on the test, but that's what we want to do. Again, I have a bar of uniform charge that is length L and total charge Q. So step one in any of these problems is look at the object you've been given and determine whether it's best suited for something that deals with linear density, areal density, or volumetric density. So if the object is very long and thin, linear density will make sense. So pick one that makes sense, though, and one that will work out the best for your problem. Again, this one, I think we can probably all say linear density will probably work the best under this circumstance. Now, that's just a start, but that tells me that I can use two things. First, I could express the linear density in terms of the ratio of the total charge to its total length. But the second thing that tells me, and the most important one, is that my sum is going to be add up every piece of the length. I'm going to say that again because you guys tend to not write down what I think are the important things. You might be listening, but pay attention. We're doing a summation here. So we want to add up every contributing piece of length to get the entire bar's contribution to the force. So when we're choosing something that's in a linear density, we're talking about adding up all the pieces of length. If we were dealing with something that had was like a surface density or an areal density, well, we would have to add up every piece of area to get the entire sheet or the entire disk or whatever the thing is. And if it were, a sphere or a cube, well, then we would be adding up every piece of the volume of the object. Each one of those poses new troubles when it comes to how do you do a sum that is two-dimensional or three-dimensional. So for the time being, we're focused on one-dimensional sums. And our job is to try and add up every contribution across the entire length. When we have decided that this object has linear density, then we're also making a statement that we're going to take this object and break it up into pieces. So I'm going to look at one little piece of the object here. I'm trying to just kind of shade it in to make sure that we're all on the same page with what that means. There we go, one piece of the object. It is that wide. That is the size of our piece. And because it's a piece of the whole object, I'm going to use dx to describe how big that piece is. Now, why x? Because it's horizontal. That's why. Now, once that's done, all I've done is I've done a small thing to try and identify where is one piece of the object. Now, there's more to the problem, things that I left off, right? Things that you're aware of from yesterday, like the whole idea of this problem was that there was a point charge right about the midpoint. I'd say that's pretty good. That's close to the midpoint. Can we all agree with that? Now, there are lots of pieces of this bar. And although this piece although the charge over here is charge Q, each one of these pieces is applying a force to charge Q. So no matter which piece I'm talking about, there's a lot of forces acting on charge Q, and they all add together to give us a net force. And I think we can all agree that that net force is likely to push the charge away. But your job isn't that. Your job is to figure out how each of these individual pieces of charge affect charge Q. So our next job is to figure out how much charge does each piece have. We're breaking this up into a bunch of little lengths, but each length has a certain amount of charge. The amount of charge it has depends on the density. So we can do a simple product. We can simply state that the amount of charge located on the piece is equal to the charge density times the length of the piece. Now, some of you coming from other courses that weren't mechanics need to understand that this is treated as a single variable. It's just saying a small piece of length, in the same way that this is kind of saying it's a single variable. It is a small amount of charge. Don't read too much into it. It has its usefulness later, but don't read too much into it. It's still kind of the delta. Because when I look at this picture here, I recognize that you could see this as x minus x naught. A measurement, you could make it from the end if you wanted. It wouldn't be convenient. But the size of this piece would be x minus x naught. Right? That's how big it is. It's a delta. We use the d because of symbology that's going to be useful for integration with calculus. But don't see this as anything more than one variable expressing a small amount of length. Everybody okay so far? Now, we're going to be using Coulomb's law, but we will need to find a way, even in Coulomb's law, to point at every single piece of this bar. And we need to decide how we're going to do that. Now, this part offers an incredible amount of flexibility to you. There are good choices to make here, and there are choices that are going to make your job harder. So what you have to do is figure out a coordinate system to overlay on top of your object. For us, it's not particularly hard because it's a one-dimensional object. Our coordinate system is a number line. But we still have to overlay a coordinate system here, a way for me to identify every single piece of the bar. Again, some choices make better sense than others. For example, there's some symmetry here that we could probably exploit. We're at the middle of the bar. So I'm not sure it makes really good sense for us to choose this to be 0. We could, but I'd argue that that will probably add a layer of complication, especially since we know in the future this distance is going to become important. So what we're doing right now is trying to figure out what's the best coordinate system that will help me identify this distance in terms of the straight bar I have in front of me. Now, there's not many options here, but there are more than one option. We could, and we didn't yesterday, we could treat each piece of the bar as a small arc length and do this in terms of angles if we wanted. It's not ideal for our purposes, but it is a way to do it. And we will see situations in which treating it as an arc length will have benefits. But in this one, I think I'm just going to treat it as a small piece of length, and I think it would make the most sense to move the origin to the place directly across at the middle of the bar. I think that would make the most sense. And I want to kind of clean this up so it looks a little nicer and actually looks like it's a bisector. So give me just a moment. There, I think that looks better. Again, we're putting a coordinate system on there so that we can kind of identify every piece of the bar. Now, with my 0 being here, I think I can address every piece of the bar. I'm using the word address here because it makes the most sense. Whether we're talking, if you've used the word address in this capacity, like for programming, where you address a piece of memory or addresses on a road, you know that if you're on a road, every house has a street address, a number associated with it. We're kind of doing the same thing here. We're trying to find a way to point out every single piece of the bar. We're going to give it, each piece, an address. The best thing to use here is something that's in terms of the variable that was chosen here. In fact, you have to try and work in the variable name that was chosen there. So I'm going to use that variable name. I'm going to call this distance from 0 to where my piece is x. What I'm saying is to find this piece of the bar, start at the middle, and go out a distance x, and my piece is a little bit more in the x direction. Everybody okay so far? We doing all right? Now on this number line, is it possible to address every single piece of the bar? Meaning, is there an x that corresponds to every single piece of the bar? I think there is. I can go on the left side by making the addresses negative, and I can go on the right side by making the addresses positive. That all makes sense? And I think my first address is 0. My last address on one side is L over 2, and my last address on the other side is negative L over 2. Does all this make sense so far? Any questions about it? Okay, so keep going. Now, once I've established those things and been given or have established other pieces that are probably going to be necessary in the course of the problem. For example, how far away from the bar I am is probably going to be necessary due to the course of the problem. My next job is to actually bring in the expression that I'm hunting for. I'm hunting for an expression here, right? There's something I want to get from this. I want to get the force on charge Q. Now, we're going to do this kind of math looking for lots of different things, not just forces. We'll be doing this to find the size of fields, the size of potentials, and in future cases, things like the change in electric potential to determine how much energy might be in a system. So this is just the start of this kind of reasoning, but it's sound reasoning for us. We're using Coulomb's law right now. So Coulomb's law has a means for us to figure out the size of a force between any two charges. That's the rule we're using. So right now, I want to bring that into this discussion, that we are looking for the force. Now, I'm going to change a little bit about how I did this yesterday because of some questions that came up at the end that I was not anticipating. We want the total force on the charge. But right now, we're only looking at a piece of the force. Again, D means a small piece of the force. Now, piece might be the wrong word to use here. It's a small amount of force, but this is the force that comes between Q and a piece of the bar. So it does not represent the entire force on Q. It only represents a small amount of the force on Q. Does that make sense? Now, I'm going to, of course, use Coulomb's law here. So real quickly, Q times dq times k. I'm putting the little times markers in there to help the folks who are having trouble yesterday identify that there's 3 different things here, but it still corresponds to Q1 times Q2 times K. All over R squared. Now, on my picture, I recognize that this is suggesting that there is a force located in this direction due to the interaction between those two charges, the piece of the bar and Q. Now, this question was asked of me yesterday by a student on their way out, and I want to kind of address it. The problem we have in front of us has symmetry, and we're going to exploit that symmetry. I think all of us realize that for every force that points at an angle to the left, like this one, there is a equal and opposite, not equal and opposite, but there is a similar force that would be pointing at a similar angle to the right. Right, there's bound to be a piece of charge over here. And that's a certain amount of symmetry. And we can exploit that symmetry. If you didn't have this symmetry, your sum would be impossible to calculate the way that we've talked about it so far. You would have to do two different sums. One to find all of the forces pertaining to one cardinal direction, and one to find the sum of the forces pertaining to another cardinal direction. Now, if you don't understand what I'm saying here, what I'm saying you would have to do is you would have to apply a coordinate system to where the forces are acting. That would mean something like an X and a Y. And then look at all of the contributions to forces in the Y direction and all the contributions to forces in the X direction. And then once you had your component vectors for force, you could find the net force. We are not doing problems like that, at least not anytime real soon. But you're going to kind of have to do it in a simpler manner for your homework if you're going to do the harder version of the square problem. Now, I'm bringing this up because we don't have to do that in this problem, but that's what you would do if it didn't have symmetry. Our problem has symmetry. I know that for every component in this direction, there will be an equal component in that direction, and they will cancel out. So I'm not going to worry about any of the components that are in the X direction or the horizontal direction. I'm not going to worry about them. I'm only going to worry about the components in the vertical direction. But I have to worry about the ones in the vertical direction. So what I'm really going to do is I'm going to state unequivocally to the problem, to the universe, that the net force in the X direction will be 0. Because I know for every left force, there's going to be a right force. And I'm going to explicitly only find the contributions to the force that are in the Y direction. I didn't say it like this yesterday. I'm trying to say it like this today to make it very clear what we're doing. So that means if I consider the X direction to be along this line, the Y direction to be along this line, that I'm going to be looking for the components of the force that are in the Y direction. But this is the total force here. Everything going okay so far? We doing all right? Well, this angle, I'm going to call theta. And I'm going to note that the cosine of theta would be the component in the Y direction divided by the whole thing. This is how cosine works. We all okay with this? So, in order to get the components in the Y direction, I need to take my full force and scale it by the cosine of theta. This is the full value of the force. I'm going to need to scale it by the cosine of theta to make it just the part of the force in the Y direction. I didn't just tack on a cosine. I changed what I was looking for. I'm now looking for the forces in the Y direction. That means I use the cosine. If I was looking for the forces in the X direction, I'd use the sine. Does everybody understand? Now, again, I'm going very slowly, and that's intentional. Now, here's the thing. Do you understand from looking at this picture that every time I change x, I change theta and I change r? Does everybody see that? All right. Well, here's the thing. In order to address every single piece of charge, I have to change x. If I want to do this sum, I'm going to have to do it in such a way that everything is in terms of x or a constant. For example, r changes every time x changes, but does z change every time x changes? No. So I can put this in terms of x and z, and that would be okay. Every time x changes, theta changes. Does every time theta change, z change? No. So what I'm seeing here is that if I can find a way of expressing cosine theta in terms of x and z, that would put a constant and x in place of cosine theta. And if I can find a way of expressing r in terms of x and z, that would replace r in terms of x and a constant. And I'm going to have to replace dq with something that has x in it, so that everything in here is in terms of x, a single variable that relates all these things together. So I have to go piece by piece and find substitutions so that all I'm left with is a single variable. Because right now I have no way of adding up all the q's because I don't know how much charge there is for each q. I've based the charge on how big the piece is. Something geometrical, something that has boundaries. 0 to L over 2 in one direction and 0 to L over 2 in the other direction. And there's no way for me to address how big theta is in terms of q. Q is how much charge there is. But there is a way to address theta in terms of x. So that's why everything is going to be terms of x. So I see several substitutions. And rather than put them into the equation right away, I'm going to identify them with you, like we've done in the past. For example, r is right here. Using the Pythagorean theorem, I can state that r squared equals x squared plus z squared. That one's easy. That's simple, straightforward, right? Also, dq, I already have this one. It's written someplace else, but I'm going to write it again. Lambda times dx. That's going to get x in there for q. Doing good so far. One more to come, right? We have to deal with cosine. Using geometry, recognize that those two angles have to be equal because they are vertical angles. And I can plainly see that the cosine function would put z over r. So cosine theta would be z over r, but I have an expression I just found for r, so I can also sub again. We doing okay? All right, so lots of substitutions to do here. And it's not going to make this look prettier, right? It's going to make this thing look like a mess. That's okay. I'm okay with this. Now, to do the next part, I need more space. So I think I can just slide my picture to the side, and I'm going to work in the space that I've made here, okay? This is a lot. So let's start with q times lambda times dx times k. That's the substitutions in the top. X squared plus z squared. That's my substitution for r squared. And z over the square root of x squared plus z squared. Look, I know what this looks like. I know. But ultimately, this is how this is done, and we are 90% of the way through it. The only thing to do now is to maybe clean this up a little bit, combine like terms, and then isolate the constants away from the function. So I want to do that first. Let's find the things that have nothing to do with x and can be isolated, pulled out front. Knowing my math skills, I know I can pull this q out front, right? It's multiplying everything in the problem. It has nothing to do with x. I can pull it out front. Lambda, I can pull it out front. It has nothing to do with the problem. It has nothing to do with the function. It has nothing to do with x. K, pull it out front. It has nothing to do with the problem. Nothing to do with x. All of those things are just constants. They're not changing. Because, and this part is new to you, the only thing that matters is the part of the function that has to do with x because of dx here. Because we've said we're adding up every piece of the bar, and x determines where the pieces of the bar are. Anything that doesn't change with x is a constant and can be taken away, can be pulled out. So those things can be pulled out. Z could also be pulled out. It doesn't change. So out front, I have q times lambda times k times z. And what's left, I want to combine together. I'm going to have dx on top. And in the bottom, I have x squared plus z squared to the 3/2 power. All right? Any questions about this to this point? I mean, I know you probably don't know what to ask yet, but I'm still going to say it like that. Yes, Owen.
Hansa first. Sorry, I just looked behind.
Wait, the 3/2 is outside because you have to square root it, and then there's a square, and then there's a.
This is to the 1 power, and this, everything in here is to the 1/2 power, and 1 plus 1/2 is 3/2.
Oh, that's right. You have to explain
Is that okay? Does everybody follow that? Okay. All right. And now I have to let Owen ask a question.
That was pretty much my question.
Okay.
Not exactly that, but pretty much.
Now, this next step generally earns you a point on the AP exam, and it doesn't cost you anything. Meaning it's not something that you need to know any math to do. The only way to actually find the answer is to now sum everything up. You have to do a summation. In algebra, you can do summations using the summation symbol and literally make recursive formulas or just add up all the pieces. We can't do that here because dx is a very small amount. We're making small incremental changes. And we didn't break it up into a finite number of pieces. We broke it up into an infinite number of little tiny pieces. That's what calculus is doing. So the symbol we use to sum is a script S that looks like that. It's the integral symbol, but it's supposed to be an S. And we're going to take the integral of both sides. Now, in doing this, the left side is just really there for show. Technically, it's not. We'd assume that this is a f to the 0 power, and we are going to do some fancy math on it. But the left side is just saying add up all of the contributions to the force in the y direction, because that's going to give you the total force in the y direction. So the left side is largely ornamental. We are doing this to make sure that we are doing our algebra correctly and that I am doing the math part using all of the math rules. Okay? But I'm adding up every contribution to the force. This is going to leave me with the total force in the y direction. The right side, though, I have to be more specific. This is not an open integral. This integral has boundaries. The words are definite and indefinite integral, and you're going to get there someday. But for those of you who aren't there, all you have to do is tell it where the first piece is and where the last piece is. Now, the first piece is all the way on the left side, negative L over 2. And the last piece is all the way on the right side, positive L over 2. You put it at the top and bottom of the definite integral to bind the integral together, to put boundaries on it. Because we're telling it where the pieces are. And we're telling it where to start and where to end. Now, here's the thing. Those of you who have been through calculus probably know this is a challenging integral to take. And I'm not saying that you shouldn't be able to do it. What I'm saying to you is that the actual process of taking this integral is actually tough. And you won't learn it till late into AB. You'll learn it December-ish if you're in BC. But this one's a toughie. You're going to have some weird stuff here. Tangents and stuff show up. Doesn't feel like it should, but it will. On the other hand, you're given an integral table. If there's an integral on the test, the integral table will have that integral in it, meaning there will be a table that will have x squared and z squared in it if you need that integral, and it will tell you what the antiderivative is of that function without you having to know it. They are not doing calculus, and they're not testing you for your calculus skill. In fact, on the AP exam, what's the most likely way they'll do this question is set up the integral that could be solved to find the net force on a charged particle. And this would be the extent of it. You would be done the moment you put the limits on your integral symbol. We will go farther. I want you to know more things. And so we might learn things that are a little outside. But this integral, this one's a toughie. I would not burden you with that today. Yes, ma'am. In talking about symmetry, oftentimes there's an easier way to do a sum, especially one like this that has equal amounts of bar on both sides. Can you all probably agree that half the bar would provide half the force? If you can see that kind of symmetry and you have that kind of symmetry, then you can rewrite this from 0 to L over 2, but then you have to multiply the whole thing by 2. Because that's only going to be half of the force. Now, some of you may be wondering, why would you do that? This already looks like a giant disaster. What does that do? Truthfully, it does quite a bit. Because as you guys are probably aware, you can work a 0 into a problem that usually is easier math, right? Also, it tends to get rid of things that are, I would call symmetry errors or parity errors, especially things that deal with trig functions, where you might get a 0 for your answer, but that only because sine and cosine have repeated values over time. So this helps with that and simplifies your problem. Also, I want to point something else out to you. This is something that you wouldn't necessarily know either, but anything that's not changing with respect to x isn't actually part of your problem. So the integral is actually simpler than it looks. Not simple, just simpler than it looks. The only thing that's actually about the integral is the stuff that's not constant. All of this are constants. Now, that was a lot. And like I said, you are effectively at the answer. Now, there's more work to do here if you want the actual expression of the answer, which would mean taking the antiderivative. And I also want you to know that this particular one is challenging because of what you have to do to get the antiderivative. But this is what we have, and it's okay. If you can get this far, you're there. Now, I'd argue for anybody in the room, this is a whole lot to do. A whole lot to do. Okay? Now, we've done one. Worked it all the way through. Slow and meticulous-like, right? I want to set up, but we will not have time to do another one. But this next one, we're going to do all the way through, including the calculus portion. Okay? And to do this one, I need a little bit of assistance to make it look right. So just give me a moment to draw this. I know that I will run up against the bell here in a minute. All right. This is from the AP exam, this problem we're going to have. I've drawn a bunch of extra stuff here to kind of help me out and get it to look the way I want it to look. But I don't need that, and I don't really need the circle either. It's just important that you know that this whole thing is based on an actual circle. Oh wait, I needed one more thing. Sorry. I need a dot. There we go. So now, get rid of that, leave that, get rid of the circle. Okay. So what if I had a arc of charge? A small piece of charge that has been bent in the form of an arc. Let's say that this distance is capital R, which would be the radius of the circle, and that the bar has some symmetry. That symmetry has to do with the fact that there's theta worth of angle at the top and theta worth of angle at the bottom. So the whole arc is measured at a segment of 2 theta of the circle. And let's say that that arc has charge value Q. If I place a charge Q at the center of the arc's circle, there would be a force of repulsion between the bar and the point charge. And there's a certain amount of symmetry here too. Wouldn't you agree? This is our next problem. I want to find an expression for the size of the force on Q in terms of theta, Q, Q, and R. All of it can be in our answer. All right? Set of steps. Now, if we start at the beginning, step number 1 is to determine whether I can use a linear density, a surface density, or a volumetric density to describe the shape of my object. Which one do you think would work best?
Linear.
Yeah, I think linear density is going to work best. This is clearly a kind of a linear shape. Now, this part might be harder for you. Can somebody come up with an expression for us to use for our linear density? Yes, sir? Lambda d theta. What do you guys think? I just want lambda, so probably not. Well, remember, it's the total amount of charge divided by the total length. The total amount of charge is Q. Can somebody tell me what the length of the bar is in terms of what's given?
2 theta.
Close.
1/4.
close. Maybe you two can get together on this one. 2r theta, that's right. All right, so if you don't know, arc length is just the angle subtended times the radius. That gives you an arc length. That's why the circumference is 2 pi r. The whole angle of that arc is 2 pi going around the whole circle. So it's the angle amount times the radius. Of course, I put a Q there, and I don't know why. But to do this correctly, of course, you would have to be given your theta value in radians. That's the only thing you have to be careful about. All right, that's not bad. So I'm going to identify a small piece of my arc. And because I like you guys to be, learned people, arc lengths are usually given in terms of s. So I'm going to call this piece ds. That's how long the particular piece of arc is. All right. Now, I like this problem for a lot of reasons. One, it's accessible. You might not see why it's accessible, but I think you will. First, does it occur to you that every single piece of the bar is the same distance away from Q? So our denominator, I'm looking at the future of this problem, our denominator is just going to have r squared in it because every piece is the same distance away. Now, that's going to make it a little easier on us this time because last time every piece was a different distance away. This means every piece creates the same size force. Unfortunately, every piece acts in a different direction. So we still have the directional problem, but we don't have the distance problem this time. That will make this a more accessible problem. So let's first recognize that I'm probably going to need to deal with the fact that that is my distance, right? That's going to be the r between my charge and my other charge. So this ds is also got a small amount of charge associated with it, dq. In fact, I think we can say that dq equals lambda ds, just like before. Not quite done yet, but we're getting close. I think the next thing I'm going to have to do is look to see if I can come up with a way of addressing every single piece of arc. Isn't that what we do next? Interesting thing, though, here. Would we address it by saying that this is length s? Would that be okay? We could, but I think we'll have a problem in the future if we do. Is there another way to address it? Yes, sir. Now, theta is a given value, so I'll need to use something else as a placeholder for angle. But I think it might be best for us to address it by addressing the angle to each one of these pieces. What's that? No, I want to stay away from theta completely. Theta is a fixed variable in the problem, so we'll use maybe just another Greek letter, just something else to stand for the angle. Don't hurt yourself too much. It's not that big a deal. But you don't want to use you don't want to use one of your constants as a pointer variable, which is why I chose theta on purpose to get us to break the mold a bit.